Hello and welcome. This is section 7 of chapter 15 on damped oscillations. And this slide starts out by saying that an oscillator that runs down is called damped. And damping is a very proliferous phenomenon in all of science and engineering because all systems eventually run down. And this really extends the idea of dissipation, energy loss into thermal energy. And so I want to continue this discussion from this mechanical perspective of oscillations. Certainly an example would be the shock absorbers in the car where those are heavily damped so that the thing doesn't oscillate. Another example that you might not think of is a screen door. When you open a screen door, either at the top or the bottom, it has the tube, and it's designed to swing back. It's designed to swing back when you push out on it. So there's a restoring force, particularly a restoring torque that's exerted on the door. And if it's damped too large, if it's too tight, the thing will just swing back very fast. We've probably all had these experiences where the door is so over damped that it just slams on you when you try and open it or when you try and walk out of it. And so they have to design those to be just right so that it slowly falls down but doesn't want to just kind of swing back on you. So that's an example of damping. The model that we'll use for damping for not only how spring masses on a spring, but also the pendulums is a linear drag force. A linear drag force is the best model to understand a simple description of damping. And so, of course, we start with the model of the mass on a spring. It's still a frictionless surface, a frictionless horizontal surface, and the spring is still an ideal spring anchored to the wall with this specific spring constant, as usual, mass m. But now we're going to turn on a drag force. We're going to have an interaction of the mass with the atmosphere. And again, that force is given by it's directly proportional to the speed. You might remember in chapter 6 that the book introduced a model of drag that was proportional to v squared. When it had the density rho and the drag coefficient c and the cross-sectional area a. That's not the model we're using. We're using a linear drag model. Some end of chapter problems in chapter 6 handle this linear drag model, which is very appropriate actually for very small objects that move in the air, like dust particles or even bugs, or on the other side, even like small viruses and small molecules, relatively bigger than the air and nitrogen molecules. So it's a good model to describe an object moving in air. It's a great model to describe how this system, macroscopic system, runs down. So if you look at the forces, now the directions, one thing that can confuse folks is that the direction of these forces, depending on the case, depending on the situation, might not always be in the same direction, right? In this case, in this snapshot of the motion, the box is moving to the right, so the drag force points to the left, but the spring force also points to the left because the spring is stretched. I mean, once the thing turns around and starts heading back towards the equilibrium, the direction of drag will switch, but the spring force will stay there. And then those signs, different parts of the motion will cause these things to be different. But the acceleration should still always point towards the center. F net should always point towards the center. So no matter the relative signs of these two vectors, the acceleration is always towards the center. And so when you sum Newton's laws, you find that the m times a is actually proportional to v and x. If I were to quickly annotate directly below this line, I'll get something like ma with the subscript, maybe m sub ax equals minus kx for the displacement, and it could be even minus b times v x. And so I have an equation. Newton's second law gives me an equation relating position, velocity, and acceleration. And there's certainly not anything like that we've seen before. Rewriting it, actually, we get an equation expressing acceleration and velocity as their respective derivatives of position, we get m times d squared x dt squared, and solving it all onto one side, plus b times dx dt plus kx equals 0. And that might be a way of looking at it that a more advanced class in differential equations would analyze this problem. Certainly, all engineering majors will eventually get to this point where you analyze this this system from this context, and you actually go through all the mathematics to derive really the equation directly below it of position versus time. So that's just a little extra for us to recognize that solving this equation, analyzing the system mathematically is a bit too hard at this level, and so we're just going to refer to the answer. But you will get to it when you take an advanced mathematics course like differential equations. So let's look at the solution here. The solution, we have that initial amplitude, the amplitude that's at the very beginning, but then you see that the amplitude decreases according to this decreasing exponential, which means the amplitude is gradually going to 0 as the particle is still oscillating around its equilibrium spot. Of course, you still got the phase constant there because you could be starting the stopwatch at different times. So the angular frequency of this damped system is going to be different than the angular frequency of the undamped system. If you look here at this equation for angular frequency, once again, derived in an advanced course, you see that the angular frequency of the damped system is really proportional to the angular frequency squared of the undamped system minus this small contribution due to the drag constant in the mass. And so what this means is that the damped system has a smaller angular frequency and therefore a larger period, right? Because period and frequency are inverses of each other. They might include the 2 pi if we're talking about omega, or might not in the case of f. And so, well, yeah, what that means is that the period is a lot shorter for the undamped system. And that should make sense because the object doesn't have to interact against the environment, against the atmosphere. The spring with the drag force is constantly fighting against the drag force, so its motion is not going to be as fast. And so it's going to take longer to make a complete oscillation. Another remark that I would make is that this discussion actually extends completely one-to-one to analyzing the damping of a simple pendulum. The only difference is that, instead of x, it would be like a displacement along the circle. The formula would be exactly the same, except the angular frequency would instead be, it would still have the b squared over 4m, but it would actually be g over L instead of k over m. So that's the one difference that the simple pendulum would have when you do this analysis. And that's why they have it be more like that. That's omega squared. So in looking at the solution, the next slide shows the solution of it. We see that this is what the graphs would look like. Now, so that means if the graph was not damped, it would maintain its amplitude the entire time, and it would be a lot more squished. The graph would be a lot more squished because the period, again, is shorter when there's no damping. It takes longer for the spring or the pendulum to make an oscillation when it's constantly fighting against gravity, or when it's constantly fighting against drag, excuse me. So that's what the graph looks like. It's kind of trapped in that magnitude of the exponential decay. And so since the position's constantly decreasing, the amplitude is also decreasing, and that's going to affect the energy. So in looking at this graph over here, we can, for a simple, for a sample oscillator, you can see what the energy of the system looks like, or the energy of the mass spring system, what that looks like as a function of damping constant in time. So you see that the energy is exponentially decreasing since the amplitude is decreasing, the energy is also decreasing. This is a graph of the amplitude as a function of time, which we have up here. And we see this energy graph down here, this next slide. So it's also decreasing exponentially as well. And this is more of a general statement about the ubiquity of exponential decay. Exponential decay is many other different places, not just damping. You know, the one example that we always use is radioactive decay, but other more common examples like terminal velocity. Terminal velocity is another example of exponential decay, or coming to rest when you're subject to a drag force. There's many examples of exponential decay. And so moving on. Now we see the graph of energy that I had been referring to in the previous slides. Energy is decaying exponentially, and so you can see this. This is good. This is a graph that's pretty general, because anything that undergoes exponential decay is defined by something called the time constant, Greek letter tau, not to be confused with torque. So after one time constant, the energy has decreased to about 37% of its initial value, which that 37% really is just 1 over E, 1 over Euler's number. And then after 2 time constants, it reduces to it reduces to 37% of that number, which is 13% of the original number, and it just continues. So the energy is decreasing in a damped system. And so that actually concludes this section on damped oscillations. You will see damping in many different forms throughout your studies in science and engineering, because it's really the most realistic type of oscillation that we observe. So if nothing else, thanks for your time, and we'll see you back here for the next video. Take care.